Okay, so starting with the page that says Bohr diagrams, I had one person this morning squeeze the Bohr diagrams into the little Lewis diagrams page. So starting with this chunk that says Bohr diagrams, we're going to review how to draw some Bohr diagrams. Now, depending on who taught you in grade 9 and 10, Bohr diagrams take on slightly different views depending on who taught you. Some teachers just put the protons in the nucleus. Maybe in grade 9 they had you put the protons and the neutrons in the nucleus using the atomic number and the mass number to figure out the neutrons. We already know how to figure out neutrons. We practiced that when we did our atomic notation, so I'm not interested in the neutrons, all right? Some teachers have you put a full circle around there and put little dots on the circle, and that's great, and that's an important way of doing it because it does show you on how the electrons are distributed, but again, you've seen that in the past. For my Bohr diagrams, very easily and very simply, and I wonder if black is actually black. Yes, it is. Excellent. So very simply and very easily, in the space for your hydrogen atom, I would like circle, number of protons, there's your nucleus, so the atomic number essentially, a semicircle with the number 1 representing the first orbit and representing that there's 1 electron in that orbit. Okay? So then all the way to the other side, and I don't have a whole lot of room here, but I'll move all the way to the other side, your version of helium plus 2, 2, and there we have our Bohr diagram. And hopefully, from what I've explained in terms of Bohr's atom, that orbit is full. We head back to the other side, lithium plus 3, 2, 1. Yes. And working my way across here, beryllium in the beryllium spot, plus 4, 2 in the first orbit, 2 in the second orbit. 4 electrons and 4 protons. If you understand and see the trend, continue to work your way across the table. Eventually, I want you to ultimately get to calcium, all right? So you can continue with that. I'm running out of room here. I'm going to just put a squiggle here, and I'm going to jump all the way over to neon. All right? So I'm jumping all the way over to this one here, which means when I get to neon, it's going to be plus 10, because that's the atomic number, 2 in the first orbit, and 8 in the second orbit. And then on to sodium, plus 11, 2, 8, 1. Maybe to just clarify, this was lithium. This was what, beryllium? That one was neon. And this one was sodium. Now again, I'm going on the assumption that you've seen this 2 times at least in the past. This is the 3rd time. If you don't understand where something comes from, by all means, it's my job to take care of that right now, but I think this is review. We're pretty well not doing anything fancy here. Just let me know if we're still not sure where these numbers are coming from. And the reason we're going to stop at calcium, we've recently learned that in the 3rd energy level, there's actually 18 electrons that can fit in it. We actually put these 2 in the 4th, but then these guys have them put back into the 3rd, and then their Bohr diagram really doesn't make a lot of sense to being able to explain how elements bond and react. So their chemistry is a little different, and even further down, even more complicated. We're just going to be dealing primarily, when talking about bonding, elements in groups 1 and 2, and then 13 to 18. We will use some of these guys in here, but I would never make you draw a diagram like a Bohr or Lewis diagram of a cobalt, because it's not a simple thing to do. You really can't do it with the theory that we have. What do you notice about the number of energy levels for elements within the same period, right? Remember, period is across, So what do we notice about the number of energy levels for elements within the same period? What do you notice? Carissa, what do you got? The same number of orbits or energy levels. That is exactly correct. What happens to the number of energy levels as you go down a group? So if we move down a group, let's say we choose group 1 and you look at all your pictures and we move down a group, what happens to the number of energy levels? Yep. It increases by 1. And hopefully you've noticed, what does that period number represent? So if we look at all of them in the third period, what do you notice about all those elements in the third period? What does that period number represent? Yep, Lily? The number of energy levels. All right? So if I'm talking about something in the third period, right? 3 down, it has 3 energy levels or 3 orbits. Okay? Or 3 shells. They all mean the same thing. What do you notice about the number of electrons in the outermost orbit for elements in the same group? So again, if I choose group 1 and I look at the outer electrons, what do you notice about them? Yep, what do you got? They're all the same number. Excellent. And how does this compare to the group number? So if it's group number 1, and if it's group number 2, what do you notice? Yeah, so the group number tells us how many outer electrons there are. And that's very important. Again, hopefully this is very much review, but what we need you to take from this is the period number tells you how many orbits it has, and the group number tells you how many outer electrons there are. Okay? 1, 2, we're not going to worry about these because the way their electrons are in orbits are a little different, but essentially 3, 4, 5, 6, 7, and 8. We're okay with that? All right? The first thing I want to do is I want to define a term called valence, all right? And maybe something called the valence shell or the valence energy level. I'm going to go with valence shell. What is the valence shell also known as? Yep. It's the outer shell. It's the outermost shell of the atom. Excellent. The outermost shell or energy level. The outermost shell or energy level. Excellent. And I'm going to just put one more here as well. The valence electrons. So if I'm talking about the valence electrons, yep. Yeah, it's the number of electrons in the outer shell. Excellent. Number of electrons in the valence shell or outermost shell. All right? Let's now continue on and talk about the Lewis diagram. So you can flip your page to the side. Bohr diagrams are great and all, right? Bohr is just a fun name to say. But in actual fact, it's got a lot of information we don't need. It turns out that the inner electrons don't participate in bonding. They don't have the power to bond. They're not valence electrons. So when we want to talk about chemistry, we don't care about the inner electrons. We only care about the valence electrons. Also, to write the number of protons is kind of a pain because the number of protons tells us the number of protons, but if I put the symbol instead, right away I know what atom I'm dealing with. So the symbol is better than putting the number of protons. So Lewis diagrams, we simply put the element symbol on the inside and we put just the valence electrons. So for hydrogen, a dot. That dot does not have to be in the 12 o'clock position. It can be at the other positions that we'll review. But for now, we'll draw it there. It's in group 1, 1 electron in the valence shell. Away we go. Off to the other side, helium. Now, you may have learned to spread those electrons out because they repel each other. There are other rules that govern where electrons go. We will learn more detail about that in grade 12, but it turns out that when you get to the filling of an orbit, electrons will actually start to pair up. all right? Has to do with their spin, because they're actually spinning as they go around, and they make a little magnetic field, and then that little magnetic field interacts with the other one, and you don't have to worry about it. Blah, 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 blah. But they do pair up at some point. Moving back to lithium, Li, single dot, all right? Moving over to beryllium, Be, and now we don't pair them up, all right? I already sent it down, all right? So we don't pair them up. And that's because within the 8 orbit, there are actually 4 little sub-orbits. You don't know about that yet. You don't have to worry about it. But they stay separate for 4 until you get to 5, and then they start pairing up, all right? So it's like there's 4 little sub-rooms within that 2nd and 3rd orbit, okay? So, jumping across the transition metals, and I'm just going to put a break in here. I get to boron. How many dots? 3. Carbon, how many dots? 1, 2, 3, 4. I don't pair them up yet. Like I said, 4 subrooms, and they're separate. After carbon, we've got nitrogen. How many dots? 5. 1, 2, 3, 4, 5. Oxygen, how many dots? 6. If you know the way they pair up, you don't have to go around in circles, 4, and then pair them up. We're going to have 2 pairs and 2 that are alone. Fluorine, 7. 3 pairs, 1 that's alone. Doesn't matter which one is alone. And I'm out of room, neon, all paired up. Okay? Moving on to sodium and A, single dot. And just one last thing, in order for you to do the extra ones at the bottom, even though I am dealing with maybe elements down here, we don't worry about the transition metals. So if I wanted to talk about bismuth, what would the Lewis diagram of bismuth be? What would the Lewis diagram of bismuth be? How many dots? Yep, 5 dots. It's going to look just like a sodium except with Bi in the middle. 5 dots means 1 pair and 3 lone. Okay? We can't really draw Lewis diagrams, again, simply of the transition metals, so I won't be asking you that type of thing. Groups 1 and 2, and then 13 to 18.